Hello everyone, welcome to another video of the course. Let's start by solving the problem number 5. So here is the problem. The magnetic circuit of figure P1.5, this one, provides flux in the two air gaps. So here we have one air gap. This is the gap 1 between B and C. And here we have another air gap, gap 2, between F and E. The coils N1 and N2, N1 is 700 and N2 is 200, are connected in series and carry a current of 0.5 ampere. So these two coils are connected in series, and so the current is the same. The amplitude of the current is 0.5 ampere. Neglect leakage flux, reluctance of the iron. Okay, so when we neglect reluctance of the iron, it means the permeability, its permeability is infinite, and fringing at the air gaps. So we have three important assumptions. Determine the flux and the flux density in the air gaps. So how we can solve this problem? Here you can see the image. Let me copy it here. So first of all, we should draw the equivalent circuit of this structure. As you can see, the direction of the current for the coil 1 is in this direction. So the field that is generated by the coil 1 is in this direction, right hand rule. And the direction of the current in the coil number 2 is in this direction. Okay, so the field that is generated by the coil 2 is in this direction. So what is the equivalent circuit? Actually, we have these two magnetomotive force sources. They are in opposite direction. Yes, because of this reason, the direction of the generated field by these two coils. And we have one air gap reluctance here. The reluctance of the iron part is 0 because of this assumption, infinite permeability. So we have one air gap reluctance here and one air gap reluctance here, or gap 2. Because we neglect the fringing effect at air gaps, so we can calculate air gap area and air gap area 2 cross-section areas using these dimensions that are given in this figure. So we can calculate reluctances and then we can solve this problem, this circuit. So what is the phi in the gap 1 is N1 minus N2 times I, the net magnetomotive force, divided by R gap 1. And we can calculate the phi gap 2 using this equation. So not too complex. And when we calculate the flux in the gap 1 and the flux in the gap 2, we can calculate flux densities. So Let's solve this problem in MATLAB. This is the problem 5. So let me copy the code that we wrote for the problem 4 and paste it here. What are inputs? Mu 0, the value of the current, the value of the coil current is equal to zero point 0.5 ampere. This is the current of coils. We know that coils are in series connection. So we have the current and we need to have the thickness of the air gap. L gap 1 is 0.05 centimeter, this number. So we need to know the L gap 1. This is the air gap length. Air gap, or this is better, length of air gap 1. The unit is centimeter, 0.05. It is given here. L gap 2 is 0.1 centimeter. So we have L gap 2, that is 0.1 centimeter. And we have other dimensions. L1 is equal to L2, L4, L5. It is equal to 2.5 centimeter. So this one, L1, L2, L4, and L5. But in image, they are different, right? So L1 is lower than L2 in image, but here they are equal. Anyway, they are equal to 2.5 centimeter, but L3 is higher. To calculate area of gap 1, we need to know the L1. Okay? And we get for the second gap, we need to know L5. So here I can write this one, L15. That is L1 and L5. They are equal to 2.5. So this is L1 and L5. The unit is centimeter. And here the depth of the core is 2.5 centimeter as well. So the depth of the core here, depth is 2.5 centimeter. So this is the depth of the core. So what are the number of turns? 700 and 200. So this is 700, 200. And now we can calculate reluctances. So we don't have this BH data. We used it for the previous problem. And let's calculate the outputs. We need to calculate area of gap 1. So this is actually, let me write here, AG1 is equal to depth times L15, L1 or L5. These are equal, right? This is L1. The width times the depth is the cross-sectional area. This is cross-section area, cross-section area of gap 1. The unit is meter square. So we should multiply this by 1e minus 4 because this is in centimeter and this is in centimeter. So we should multiply it by 1e minus 4, and this is the area of gap 2. Okay, so as you can see here, the cross-sectional area of gap 1 is the same as cross-sectional area of the air gap 2 because the depth is the same, and also the L5 and L1 are the same. We didn't use L3. Why? L3 is used when we assume a value for the reluctance of the iron. So it is used when we are going to calculate the iron reluctance. But in this case, we didn't use the reluctance of the iron in our formulation because of this assumption. So anyway, we can calculate the reluctance of the gap 1 and reluctance of the gap 2, and then we can solve the problem. So here, similar to this one, let me copy this text. Reluctance of the gap 1, gap 2. This is area of gap 2. So here I can copy this. Reluctance of gap 1, reluctance of gap 2. So here also I should edit this comment. This is horizontal. If you remember when we solved this problem, the second problem. So here we have this reluctance. This is L gap 1, L gap 2. This is centimeter, and we need to convert it to meter. This is a area of gap 1, area of gap 2, mu 0, permeability of the air. So we calculated these two parameters, and then I can calculate phi gap 1 and phi gap 2. So here, let me delete this line of code. This is phi gap 1, that is equal to n1 minus n2 times I divided by r gap 1. So here I write n1 minus n2 times current, the coil current, divided by r gap 1. So this is the flux in the air gap 1. And what is the value of the flux in the air gap 2 is this one. This is the same as this one, the numerator, but we have this reluctance. The L gap 2 is higher than the gap 1, is twice, right? The length of the second air gap, this one is twice the gap 1. Finally, we can calculate the flux densities in the air gap 1 and air gap 2. So also let me delete this. This is B gap 1, that is by gap 1 divided by a area of the air gap 1. This is 2, and this is the flux density in air gap 1. The unit is Tesla. We converted units into SI units, and this is the gap 2. So now let's run the code. Here you can see the outputs. The B gap 1 is 0.62, B gap 2 is 0.31 Tesla. As you can see, the flux density in the air gap 1 is twice of the flux density in air gap 2, because this length is half of this one. So if we consider these assumptions, as you can see, we can we can determine the value of the flux density in air gap by adjusting the air gap thickness. So depending on how much flux density we need, we can determine this thickness. So now again, let's solve this problem using the finite element method and check, right, our assumptions. So here, let's close this project and define a new project for the chapter 1. This is problem 5. And add a new ANSYS Maxwell 2D design, how we can draw this geometry, similar to previous ones that we created. First, I can create a rectangle and then create another rectangles and subtract. So here, I draw this rectangle, this one. What is the x size? X size of the rectangle is L1, L2, L3, L4, L5. So most of these are the same. Okay, these numbers that we have here, but we can define these variables. So this is L1 plus, let's use capital letters, L1 plus L2 plus L3 plus L4 plus L5. This is 2.5 centimeter, L1, L2, L3 is different, is 5 centimeter, 5 centimeters, L4 2.5, excuse me, L5 2.5. What is the Y size? The Y size is not given in this figure, just we have the length of L gap 1 and L gap 2. So I can consider a square 1. So let's consider this, right, the same. So now I need to draw this rectangle 2, and here we need to set the dimensions. So we need the x and y coordinates of this point. This is L1, L1, because we considered the same dimensions. Okay, so here this is L1 and L1 here. The X size is L2. The Y size is this summation minus 2 times L1. So this is equal to this one minus 2 minus L1. Excuse me. So this rectangle that we have here. So another one we can draw here. This is the corner point is L1 plus L2 plus L3. The Y is L1. This is L4 and this is again minus L1. Most of these are the same. So this rectangle, okay, considering these numbers. So we can select rectangle 1 and hold the control key and select the rectangle 2 and 3. So let's subtract. You can see this object now. Now we should create air gaps. So one air gap here and one air gap here. So let me define this variable. This is the total width of the outer rectangle, and this is total height. We consider them the same. I want to use them here. So for this rectangle, the corner point, this is equal to 0. The y, I write here height divided by 2 minus L gap 1 divided by 2. So L gap 1 is 0.05 centimeter. X size is L1, Y size is L gap 1. Right? This is the first air gap, and the next one is this. So I can consider similar numbers. So let me copy this and paste this here. The X coordinate of the corner point is L1 plus L2 plus L3 plus L4. X size is L5. Y size is L gap 2. And this is L gap 2. This is 0.1 centimeter. This is also right. L gap 2. We have these two air gaps. So in this figure, you see exaggerated, right? Plot. So rectangle 1, hold the control key, rectangle 4 and 5, subtract. Yes. Now we should define coils, right? We have a small air gap. The air gap is very small, but here, right, we have this air gap. Its length is twice this one. For defining coils, we can use the previous method. This is, let's use this for the coil 1, and also we need to create coil 2. For this rectangle, let's set this corner point. I write the x1 equal to L1 plus L2 minus, width of the coil minus, let's consider 1 millimeter, the corner point. And X size, the width of the coil, let's consider it equal to zero point 0.8 centimeter. So this is width of the coil, and also we need to consider height. So here I used these numbers. Okay, maybe we can define a parametric structure. And for the next one, let's draw something like this and use this one. I want to consider the same width for both coils, and this is the width of the coil. The number of turns in the second coil is lower. So just these two geometries, and like before, we can duplicate and mirror these objects. So here I select this arbitrary vector, but we know that the base position is L1 plus L2 plus L3 divided by 2. Y is 0, and here is a line in the direction of the x-axis. So, okay. And for this one, for this rectangle, this is 1, 0, 0. So here you can see these geometrical operations in the history. So we have created the geometry of this example. Now let's define excitations and add materials. So let's change the colors to copper. Yes, this is much better, a better visualization. And now I am going to set the material of this object to iron. Like before, we used this material, this iron, and these are copper. Okay, so now let's define the excitation. What is the direction of the current? For this region, the direction of the current is into the paper. So here, let's select this one, assign excitation. The total current that is flowing in this rectangular region is equal to N1 times current. That is equal to N1 is equal to 700. The unit type is none, again like before. The value of the current is 0.5 ampere. This excitation that we defined. So let's copy this one, assign the current. Okay, yes. So now let's check. The direction of the current for this one is into the paper, and for this one is out of the paper. Okay, so this is the correct definition. Into the paper, out of the paper. But what about the second coil? For this region, the direction of the current is out of the paper. So for this one, I select this excitation. This is N2. N2 is equal to 200. The unit is none like before. And for this one is into the paper. This is N2. So we have defined excitations, materials, and let's draw the region. Offset equal to 100%. So let's select edges and apply the boundary conditions. Vector potential 0. So everything is okay, and we can add this solution setup and solve the problem. But we have these assumptions. These assumptions neglect leakage flux. So in finite elements, we can actually, the solver calculates all flux. By leakage flux, in this problem, it means that we have this flux, right? The leakage flux is the flux that is not linked totally and is not crossing the air gap and return. So this is a leakage flux. The finite element solver calculates this flux. Okay, so infinite permeability and fringing at air gaps. Also, the finite element calculate the fringing effect. We can compare our solution in the Maxwell with the solution that we calculated in MATLAB using analytic equations for B gap 1 and B gap 2. But we can consider a material with a high permeability. So here, the permeability of the iron is equal to 4000. So let's set the permeability equal to 100 and solve the problem. I want to compare. Also, let's define a mesh operation here equal to 3. Let's consider 2 millimeters. Okay. So analyze. Then we can visualize the flux density vectors. The solution is in process, completed. Thanks to ANSYS Maxwell software, we can solve these problems quickly, right? As you saw here. So B vectors, you can see the field, the magnetic field. The permeability of the iron is 100, is not too high. Just I want to compare, right? This is the field. And we can plot the flux lines. So field flux lines, yes. Let me increase. Here are flux lines, okay? And as you can see here, in this case, we have more flux lines because the air gap is lower and the reluctance in front of the source is lower. So let's increase the number of flux lines to 50. You can see this leakage flux, right? Calculated by the software. This leakage flux. However, they are too small. And here we have flux lines in air gap. The fringing effect is low because the thickness of the air gap is low. But here, because the thickness of the air gap is higher, we have these flux lines also. Anyway, let's consider, right, this color for flux lines. This is much better. Even if we increase the numbers to 200, so you can see more flux lines. You can see the fringing effect. However, it is small for this air gap and for this air gap. So I want to plot the By, the Y component of the flux density in the middle of the air gap. So here, if I draw a line from here to here in the middle of this air gap, we set the coordinates. Here the coordinate is height divided by 2 And this is the same, but this is L1. So this is in the middle of the air gap one. For the second one, let's draw another line here. This is in the middle of the air gap. We can set this is L1 plus L2 plus L3 plus L4. And finally, this is plus L5. All dimensions that we used. So we have added two lines in the middle of air gap, and in the calculator fields, let's define the by, the y component. So I select B and select the y component. Let's add it to named expression by. Perfect. So let's run the analysis again. So in this case, the permeability of the iron is not too high, but still you can see these flux lines inside the core. But you can compare the amount of leakage flux for this case and the case that I increase the permeability of the iron. So let's plot the By for the first air gap. This is By is in opposite direction. And for the second air gap, By is this one. What is the reason? Because the field is in negative direction of the y-axis. So here, what is the average value? Is 0.08, and the average value here is equal to 0.07. But what are the numbers that we calculated? 0.6 and 0.3. So is our calculation correct or not? We need to check. Let's increase the value of the permeability of the iron to 1000. Yes, and repeat the example. So in this case, the permeability of the iron is 10 times higher than the previous one. So now the average value of B for the first air gap is 0.38. The negative sign is not important because it is in the negative direction of the y-axis. This one is 0.22. No, this is still different from these numbers. So let's increase the value of the permeability again, 10,000 this time. Okay, and run the simulation, analyze. So in this example, you will realize that considering infinite permeability is an ideal case, right? So we neglect any magnetomotive force drop in iron. And here in this case, as you can see, when we increase the permeability, the number of leakage flux lines is lower and lower, right? What is the reason? Because the reluctance in front of the flux line in the iron is lower, and we have lower, right, leakage flux lines. So let me reduce this number to 50 so you can see these flux lines. And what is the value of By in the air gap 1 is 0.59, Okay, this number is 0.62.31. These are close now. Why? Because we considered the infinite permeability assumption. So let's consider an extreme case and consider the relative permeability equal to 100,000. So this is really high. And rerun the analysis to check the waveform of the flux densities in air gap. So in this case, when we consider a very high permeability for the iron, yes, in this case, this is 0.62, 0.62, and this one 0.31. So here 0.31. We matched the numbers that we calculated in MATLAB using this simple circuit and the numbers that we calculated by exact solution of the problem using the finite element method. So, okay. So from this problem, we can realize this point. When we have infinite permeability for iron, okay, we can consider the value of the reluctances that we have in iron equal to 0, right? Because mu is in the denominator of this fraction. In real case, we don't have infinite permeability, but when we use a material with a high permeability, we can build up a good flux density in air gaps. So yes, you solve this point in this problem. As you can see, however, these problems are simple, but we can learn these important points from these problems. So you can generate this ANSYS Maxwell file and change the dimensions because now we have a parametric design, and also change the numbers here in MATLAB. So generate different models, generate numbers, analyze, and check the solutions. Okay, for the last point, let's check the amount of the flux. How we can check the amount of the flux is the same as the Maxwell because the average value of B gap, the flux density are the same. Just we should multiply by this area. Areas are the same in the MATLAB and Maxwell. So there is no important point here. And we know that these are equal because the average values of the flux densities are equal. So you can generate this magnetic equivalent circuit in the simpler and analyze, okay, and analyze the problem, calculate flux density. So let's calculate this problem also in simpler. So from here, insert a simpler design. So let's add two reluctances, magnetoresistor and a magnetomotive force source here. Okay, and this one, let's rotate it. This is the second coil. This is equal to N1, that is 700 times 0.5 amps, I don't define variables, just I want to define one variable. And here is this one, 200. Here we have the reluctance of the first air gap, and let's copy it. We have reluctance of this air gap. So the same equivalent circuit that we have here. So in this case, we can set the value of the reluctance. What is R gap 1? It is equal to this number. This is R gap 1. And what is the value of the R gap 2? Is equal to this number. This is R gap 2. So let's add a DC solver, solution setup DC, and solve the problem, analyze. I want to calculate flux in air gap 1 and 2 using the simpler. So data table, the flux for these two elements. This is voltage second. I know that you can change the unit also here. You can specify the units anyway. So what is the value for the air gap 1? We have more flux, yes, because the flux density is higher. So phi gap 1 is, if I multiply this by 183, is 0.4 milliweber, 0.4 milliweber, right? The same. And for the second air gap is 0.2 milliweber, 0.2, close to 0.2. That is correct. So we solved this problem also using the simpler. Okay, so I think it's enough for this video, and let's continue solving all the problems in the next video. Thanks for watching.